So this is chapter 12 and 13 in the lab manual. So these are taught as separate chapters in the lab manual, but they really go well together. You can't do a 2-sample t-test without doing a variance test first. So the main goal is to do a 2-sample t-test. But there are 2 types of 2-sample t-tests, depending on whether the variances of the sample are equal. So 2 weeks ago, we went over a 1-sample t-test. The difference between a 2-sample t-test and a 1-sample t-test is that with a 1-sample t-test, you have a given population mean and then a sample. And you're comparing your sample mean to your given population mean. So in all those problems, I was like, the mean of this population before, fertilizer was added is 12.3. Or I guess that doesn't make sense. Maybe like 7.2. And then here's a sample, calculate the new mean, calculate all these statistics. Are those 2 means different? With a 2-sample t-test, you don't have a reference population. You just have 2 samples and you need to calculate the statistics for both of them. So because of this, we need to first learn how to test for equal variances so that we can decide which of the 2 types of the 2-sample t-test we need to use. So an F-test is also known as a variance ratio test. And it's a way to compare any 2-sample variances for equality. It is very sensitive to normality. We can only use the F-test if 2 populations are normally distributed, which as of now, we will assume is true. Later on, we'll do a test to see if they're normal first, but right now we'll assume that they are. And what normally distributed means, just as a reminder, if we're all not sure, is this. We need both samples to have distributions like this. And what we're testing is the variance. So let's say we're looking at the range in the data from here, right? Comparing this to maybe a population like this with the means in the center. The spread of data between these 2 data sets doesn't look equal, which means their variances are unequal, which means we have to do a specific t-test. So that's the point of this. If the variances are equal, we can do what's called a homoscedastic test, a homoscedastic t-test, where the ratio between the variances is approximately 1. So the ratio between them is approximately 1. If a ratio is approximately 1, that means that the variances are pretty much equal between one population and the second population. We can also find that variances are not equal, in which case we would run a heteroscedastic ratio or a heteroscedastic t-test. So the ratio is therefore bigger than or less than 1, but pretty much just bigger than for reasons that I'll explain in a moment. So homoscedastic is just a really fancy statistics way of saying same variances. Homo means same. Heteroscedastic there then just means that it's a fancy way of saying different variances. Hetero means different. So an F distribution is different from a normal distribution because it has this really long positive right tail skew. So we can see that, right? It's like this entire area over here. As our degrees of freedom increases, our skew also decreases. So these are inversely proportional to each other. The F ratio or the F distribution cannot be negative because it's based on a ratio. And a ratio, right, is just one value versus another value, or one number on top of another number. So because of that, it can't be negative. It's always greater than 0. And if these two numbers are the same, then our ratio equals 1. So that's when we know that our variances are approximately equal, is when they're approximately equal to 1. Our null hypothesis, when we do an F test or a variance test, is that our variances are equal. Our alternative hypothesis is that our variances are unequal. So the idea behind this test in general is if two populations from which we draw samples have equal variances, then the two sample variances should be approximately equal, right? If we draw a random, so this is a population. If we take a random sample and our sample mean is around here, and then we take another sample and our sample mean is around here, those are the means. But what we're saying is the spread of data in those samples about the same? So again, for our null hypothesis, if the variances are equal, our F calc should be approximately equal to 1. If our variances are unequal, our F calc should not equal 1. It should either be smaller or greater than 1. There are one-tailed and two-tailed hypotheses. However, for this class, we are not doing a one-tailed hypothesis. You'll see this in the lab manual, but we're not going to be discussing it, and we're not going to be going over it. I'm not going to be testing you on it. We're just going to be looking at two-tailed F-test hypotheses. So are the variances equal or unequal? So when we're calculating our F calc, our F statistic for our F test, it's just equal to our larger variance divided by our smaller variance for the two samples. That's it. So it's a very, very simple equation. For the two-tailed F test, again, the only one we'll be covering in this class, we always put the larger variance in the numerator, which means that we are always finding the right-tailed value, and which means that our ratio is always between 1 or it's always greater than or equal to 1, I should say. Right? Because if we'd put the smaller one or the larger one at the bottom, the smaller one on top, we'd be getting a less than 1 ratio. In this class, I'm going to ask that you always put the larger variance on top of the ratio and the smaller on the bottom. If you calculate an F calc and your value is less than 1, you need to switch the variances. You will lose points if you don't switch your variances. If your F calc is less than 1, you need to switch them. Okay. So when we deal with degrees of freedom, it's a little bit different than what we've done before too. Because we're dealing with two variances from two different samples, there are two separate degrees of freedom. And it's very simple. It's the same equation we've used for degrees of freedom in the past with it, where it's just n minus 1. But we have a degrees of freedom for the numerator and a degrees of freedom for the denominator. And these are represented with this like V looking character. That's actually the Greek letter nu. So nu 1 and nu 2. Nu 1 is for the numerator, nu 2 is for the denominator. There are also tables for this F ratio at the back of your lab manual. These are on page, there's a couple different ones, and you'll see why probably as soon as you look at them. Starting on page 275 to 278. Those are all tables for an F distribution. Each table, there are multiple tables because each of them is for a specific value of alpha. So each table is a different value of alpha. So when we solve these, we're actually not really going to be doing any of these by hand. You may have to for the lecture portion, but in lab, we'll be using R from this point forward. But the first thing you have to do is choose your alpha value, which I will give to you. Again, it's almost always 0.05 unless otherwise stated. Then you have to look at your F table associated with that alpha value. Find the column corresponding to the degrees of freedom for the numerator and for the denominator. And the value that you come to in the table is your critical value. These values work the same way that they did for our t-tests. If our F-calc is more extreme than our critical value, then we reject the null hypothesis and we say that our variances between the two samples are unequal. If our F-calc is less extreme than our F-crit, we say that we accept the null hypothesis and our variances are approximately equal. What's nice about these, the F-test and using the two-tailed test and always having our larger variance on top is that we can always make these decisions because when we calculate F-calc, we always put the larger variance on top. So our F-calc should always be greater than our F-crit when we reject the null hypothesis. Our F-calc should always be less than our F-crit when we fail to reject the null hypothesis. Because before, if we were doing t-tests, right, we had to deal with like negative and positive values. And sometimes like our positive value is greater than our negative value, but it's not as extreme as our negative value. So we still don't reject the null hypothesis. You don't have to worry about any of that this time. If your calc is bigger than your crit, you reject. If it's smaller than crit, you don't reject. There are a lot of untabled degrees of freedoms on these table, as you'll notice. So we go from, for the denominator, 3 all the way up to about 40. No, I guess around 20. Before past 20, we start skipping values in like increasing increments. So if you need to use the table to find your critical value, you can use this conservative critical value method, where you decrease the degrees of freedom for either the numerator or the denominator to the next lower table value. So you don't round up, essentially. You round down to the lowest or to the next available degrees of freedom. So if the degrees of freedom for the denominator was 31, if you look at the table, there's only 30 and 32. You would not use 32. You would round down to 30. This won't really be an issue in this class because we'll be doing everything in R. We use this var.test function, which gives us our F-calc, our degrees of freedom, p-value, confidence interval, all of that stuff. So we won't even need the table for that. Okay. So I'll go through a super quick worked example just to kind of get you familiar with how this works. So let's say that you take samples of 13 and 12 measurements of wing lengths from 2 different bird species. So your sample sizes don't have to be equal. We're measuring measuring wing lengths from 2 species of birds. And we want to know if the variability is the same between the 2 species, because we want to do a 2-sample t-test on these 2 species. The variables that we're given are our sample size, our means for bird species 1 and 2, and our variance for bird species 1 and 2. So the first thing we want to do is write out our hypotheses for the F-test. Our null hypothesis is that our samples for bird 1 and bird 2 are equal. The variances, not the means, the variances between the two samples are equal. Our alternative is that they are unequal. That's it. And that's always what they're going to be. We then have to select an alpha level, in this case 0.05. So we need to look at the alpha over 2 table. Again, not a huge concern because we'll be doing this in R. But we could then, using the table, look at our FCalc. So, or calculate our FCalc. So we have our larger variance, the 6.97, divided by our smaller variance, is 4.32, and we get an FCalc of 1.61. So a little bit bigger than 1. We now find the degrees of freedom for both variances. So new 1, our degrees of freedom for bird species 1 is 12. New 2, our degrees of freedom for bird species 2 is 11. We can then look up our F-crit on our alpha over 2, alpha equals 0.025 table, and we find that our F-crit is 3.43. Our FCalc is less than our F-crit, therefore that's what this 3 dots mean. It's a really common notation in math, and I use it a lot just because it really shortens things down. But it means therefore. So FCalc is less than F-crit, therefore we fail to reject the null hypothesis and conclude the variances are not significantly different from each other. Even though one is bigger than the other, we've determined they're not significantly different. That means that we can do a 2-sample t-test for equal variances. And that conclusion is the entire purpose of doing the F-test. We just want to know what 2-sample t-test we can use. So now on to these 2-sample t-tests. So we use these 2-sample t-tests to test the null hypothesis about the equality of 2 population means, or 2 sample means, is really what that should say. Of 2 sample means by drawing random and independent, or I guess I actually kind of clarify that in a second. So the equality of 2 population means by drawing random and independent samples from the 2 populations. So we draw samples from these 2 populations. We're testing, are these samples from these 2 populations approximately equal? If the samples are approximately equal, it means the population means are maybe equal as well. We'd probably take more samples to actually test that. There is also something called a paired design experiments, where we do a paired t-test. And for these, we're testing a hypothesis about the comparison of means between samples or individuals that have been tested twice. And that'll make more sense in a second. So there are different names for these t-tests. Technically, a homoscedastic equal variance t-test is called a student's t-test. And a heteroscedastic unequal variances t-test is called a Welch's t-test. And these are just named for the people who came up with them. For both of those, we need to do an F-test because both of those come from separate samples, like 2 samples from 2 populations that we're trying to see if they're equal. We need to do an F-test to figure out, are we doing one for equal variances or unequal variances? And then there's this paired sample t-test. And these paired sampled t-tests have 2 treatment groups, and the replicates are not independent. That's very important because independence is pretty much an assumption for all other statistical tests. But in a paired t-test, they are not independent. And these are usually set up as before and after type experiments, or sometimes related family members. And we do not run an F-test on paired samples. We do not need to know if the variance between the treatment groups are equal because they're being tested on the same or related individuals. When we have independent t-tests, those are our students or Welshes, are hetero or homoscedastic. Or I suppose are homoscedastic and heteroscedastic. And these are, again, two different treatment groups. The replicates are assigned independently and randomly. So that's the difference between these independent and paired t-tests. An example would be two different groups of people, men versus women, right? An example of a paired one would be one group of people before and after a surgery. So our hypotheses for our two sample t-test are pretty much the exact same thing as our hypotheses for our one sample t-test, except now we're not comparing a reference group to a sample, we're comparing two samples. So these should all look very familiar. For our two-tailed, we have our null hypothesis that our means from sample 1 and sample 2 are equal. Our alternative is that they're unequal. Our one-tailed is that either sample 1 is greater than or equal to sample 2, or our null would be that our sample 1 is greater than or equal to sample 2. Our alternative is that sample 1 is less than sample 2, or we think that sample 1 is less than or equal to sample 2, and our alternative is that sample 1 is greater than sample 2. It's a little bit less clear when we say, like, is this test right-tailed or left-tailed, right? Because sample 1 and sample 2 are arbitrary. You know, if I said, let's see, do robins have greater wingspan compared to sparrows, right? Is robin group 1, is sparrows group 2, is sparrow group 1 and robin group 2, right? It doesn't really matter. You can switch them either way. It's arbitrary. It's really just done by whichever one I decide is first and whichever one I decide is second. So it's a little bit, you can't really say it's right-tailed or left-tailed. You're saying either they're equal or not equal, or one is bigger than the other. Generally, I recommend that you use names of the populations, like a little bit more descriptive rather than 1 or 2 for subscripts, because it's a lot easier for you and for me to read and to understand what's going on. And actually, that's another really good note, I think, about the exam and things you turn in general. The more specific your answers are, the less guessing I have to do. You don't want me to guess. The more I have to guess about what your answers mean and where your numbers come from, the worse it is for you. So just a little sidebar. So when you're writing these, please write like mu sparrow is equal to mu robin, or mu robin is greater than or equal to mu sparrow, instead of just 1 or 2. It's super ambiguous when you do this. I don't know what you mean. Remember that there is also always needs to be some form of an equal sign in the null hypothesis. On the exam, a couple of people were getting these null and alternatives mixed up. So please review that. Remember, the null hypothesis has some sort of equal sign. The alternative hypothesis is the one that we're actually looking for. Okay. So remember, before we do our 2-sample t-test, we need to do our pretest, our f-test. We need to see if our variances are equal or unequal. If they're equal, we can do a homoscedastic student's t-test. If they're unequal, we could do a heteroscedastic Welch's t-test. We hope to accept our null hypothesis. We hope that our variances are equal because the homoscedastic test is actually a more powerful test. It's better able to detect differences between groups and better able to tell us with more precision if group 1 and group 2 are different from each other. If we have to do a Welch's t-test, we get more conservative results because of that extra variance. There's extra variance, therefore we can't be as sure that the two samples we're testing for our t-test are actually different from each other. So it's a little bit weaker. And the reason for that is because when we do a student's t-test for equal variances, we pool some of our values. So I know this variable for t-calc looks intense and a little scary. You don't have to do these by hand. I'm not going to ask you to solve any of this by hand in this class. Again, you may have to for the lecture, but not in lab. And it's actually not that terrible when you look at it. It's actually very similar to the t-calc that we used for a one sample t-test. So when we do our one sample t-test, so we have our we have our x bar minus mu divided by our standard error, right? And that's the same thing as x bar minus mu, minus mu divided by the square root of our variance over the sample size. That's pretty much the same thing going on over here. We have the difference between our two means, and we have the square root of our variance over our degrees, or over our sample size. The only difference is that we're adding this 1 over our sample size between our two groups, and our variance is pooled. So we're essentially kind of not quite, but kind of calculating like a weighted mean for our pooled variance. That's how I like to think of it. So if sample one has a higher sample size, that's variance is going to count for more compared to the variance for sample two. So if N1 is equal to 40 and N2, so our sample size for the second one is 12, and the variances are equal, like, so S1 squared is equal to maybe 12, which is also equal to S2 squared. Those are also equal to 12. So our variances are the same thing, right? That means right here we would have 39 times 12, but here we would only have 11 times 12. And then we add those together, right? So it's actually not that terrible of an equation. And then we'd have 39 plus 11. So it looks awful. It looks really complicated, but it's not that bad. And this denominator term is just the combined degrees of freedom. It's literally just the same thing as degrees of freedom for one plus the degrees of freedom for the other, or sample size plus sample size minus 2. So it's not bad. And then so yeah, here I actually have that in the slide written out as well. So let's talk a little bit more about this pooled variance. So every value of variance is assumed to estimate the population variance sigma squared. Thus, we should be able to get a better estimate of sigma squared by pooling sample variances from different samples. If we had rejected the null hypothesis for the F-test and found that our variances are unequal, then obviously we can't pool the variances. We already said they're not the same thing, so why would we combine them? If that's the case, and we have to do a heteroscedastic t-test, then we calculate our t-calc a little bit differently. But again, it's pretty much the same thing. So we still got the difference between our two means, x bar 1 minus x bar 2, and we've got the square root of our variance divided by our sample size, except now we have two different variances. If we had multiplied the pooled variance from the last slide into the fractions, we would have gotten pretty much the same thing, right? This is what was in the last slide. If we distribute this value into here, we get this, which looks almost identical to this, except here we have two different variances. We have these two variances compared to here, we've got the same variance in the numerator. So these equations look scary. They're not that bad. So we use the individual variances rather than the pooled variances since they're not equal. The degrees of freedom for a Welch's t-test looks a little crazy. So let's just walk through this really quick though. So we've got our variance for 1 divided by the sample size for 1, the variance of 2 divided by the sample size for 2. Add those together, square it, and then divide it by our variance for 1 divided by our sample size for 1 squared divided by the numerator, and we add those two together. Again, I won't have you be calculating this by hand. Okay, so now we're doing the actual two sample t-test. So how do we do that? First thing we need to do is do an f-test. Do we accept or reject our null hypothesis for our f-test? Are our variances equal or unequal? If our null hypothesis from the f-test is accepted, then we calculate t-calc for a student's t-test. Or if it's rejected, we perform a Welch's t-test. Finally, we have our paired t-test. And this is really looking at the difference between means of groups of paired observations. And it's actually much more similar to a one sample t-test. So, and that's because we're actually comparing our set of data, our set of differences to a hypothesized mean of 0, right? If there is no difference between before and after a surgery, the difference between before and after is 0. So what we actually do is we compare our calculated difference between before and after, or group 1, group 2, before treatment, after treatment, to 0. And remember that these observations the observation means for each treatment are observed on the same individual or sample subject or related individuals. So our hypotheses are that the mean difference, mu d, our mean difference is equal to 0. That's our null hypothesis. There is no difference between group 1, group 2. There's no difference between before and after. Our alternative is that there is a difference, that the mean difference doesn't equal 1. It's either doesn't equal 0. It's either less than 0 or greater than 0. So if we were to do this in Excel, we would have to create an additional column of DI, which is the difference between the means, or the difference between each index, and then we calculate a mean difference, which is essentially gives us a one sample t-test against our mean difference. This big ugly thing here is just the equation for standard deviation. The whole thing together is just standard error. So our t-calc for a paired t-test is literally just the mean difference divided by our standard error. N is the number of pairs of observations, right? So if you have, let's see, before and after, 1, 2, 3, 4, we have 5 pairs, and we've got numbers for all of these, which means we have 10 observations. Our sample size is not 10. Our sample size is 5. because these are paired together. We're calculating a difference for each of those. Sorry, I keep tapping the arrow key. When we calculate a confidence interval for paired samples, it's our mean difference. It's the same thing as our other confidence interval equation, except now we use our mean difference instead of our sample means. So it's our mean difference plus or minus our t-crit times our standard error. This S sub d is just our standard deviation for differences. The t-value is found from the table using the alpha over 2, and our degrees of freedom is n-1. If our confidence interval overlaps 0, there is no difference between the treatments. That's the same as from before, except it was if our confidence interval overlaps our population mean or an alternative sample mean. If our confidence interval does not overlap 0, then there is a difference between the treatments. We are 95% sure that the actual mean difference between treatments is not 0. However, we really don't calculate confidence intervals for two-sample t-tests, just in general. So you can breathe a little bit easier that you won't have to be doing that so much. And then finally, I think this is just about the last slide. I have a flow chart for you. So this makes it really, really easy to figure out what test you should be running. So are the data values paired in some way? Yes, do a paired t-test. If they're not, you have to figure out, are the population variances known? If the variances are known, you do a z-test. You need to use your z-distribution. If they're not, which they probably aren't, you have to ask, are your population variances equal? If they are, you do a student's t-test, which is homoscedastic. If they are not, you can do a Welch's t-test or a heteroscedastic t-test. Technically, you can also use this Welch's t-test even if your population variances are equal. Because it's a more conservative test, it doesn't mean it's wrong, it just means that it's less powerful. In this class, if the variances are equal and you do a Welch's t-test, I will mark you as wrong, because I am asking that you calculate if the population variances are equal and then do a student's t-test. So don't try just using Welch's t-test for everything. I'm teaching you a student's t-test because I want you to use a student's t-test. So the last thing is just some important takeaways from this. The null and alternative hypotheses. There are null and alternative hypotheses for the F-test and for the t-test. I'm going to ask that you write both of those, and I have places for you to do that. But just be aware that there are two sets of null and alternative hypotheses, and I want you to know them both. And then I had you do this on the exam. You also did this on the in-class assignment where we were doing t-tests. I had you write the statistical and biological conclusions. Your statistical conclusion is, I'm looking for two things. Do you accept or reject the null hypothesis? And why do you do that? Are you comparing your calc and critical values? Are you looking at your p-value? Is your p-value greater than or less than alpha? Those are the two pieces of information I want you to give me in the statistical conclusion. Accept or reject, why are you doing it? For the biological conclusion, bring that back to the actual question. Biologically, let's say robin wings are greater than sparrow wings. What does that mean? I mean, I guess you could say just that the test shows that there is a significant difference between sparrow and robin wings, or that sparrow wings are significantly longer than robin wings. And that's it. That's really all I'm looking for the biological conclusion. But, you know, just bring it back to the actual word problem. What was this test done on? So that's it for the explanation in the PowerPoint of why of everything. There are more slides in the actual PowerPoint that I hid for the presentation. It's like more of a walkthrough through all of the calculations for these examples, some of the worked examples. But kind of, I guess, like as a compromise between those comments I was getting about the slides taking too long, I cut those out, but you have them. If you download the PowerPoint, you have all of that stuff. But instead, I'm just going to go straight into R today, and we're going to get started there. So, okay. Are there any questions about F-tests, two-sample t-tests, paired tests, any of that stuff before we get into R? Okay. No questions. Great. So hopefully everybody got their RStudio working or their RStudio Cloud account working. I'm going to be using RStudio Cloud just because there's a couple extra steps if you use RStudio Cloud versus RStudio. RStudio is a bit more streamlined. So if you want to use RStudio, that is totally fine. And it doesn't crash your computer or doesn't like get any weird issues. This is really only a problem for Macs because of the new update. That's fine. Anytime I say if you're using RStudio Cloud, you need to do this first, just ignore that, obviously. Okay. Sorry, dog is barking. I don't know if you can hear that, but okay. So first thing you got to do is go to RStudio Cloud, rstudio.cloud. Hopefully you've already made an account. I'm already signed in and ready to go. I made myself a project folder with my Bio 260 Fall 2020. It takes a little bit of time to load. Okay. But hopefully, once you open this, you probably won't have anything because I don't think you've probably loaded anything in yet. So this should probably just be a blank workspace. You'll need to make a workspace. When you open it, though, this will all be blank. This will just be like this, and this will be blank for you. For RStudio Cloud, you can't just use the files from your computer. You need to upload files into the cloud first to access them. So to do that, you need to click on this upload button. When you do that, you should get this upload files, target directory, all this stuff. So the target directory, oh, I already said that. So I'm going to choose browse. Oh, actually, this is from my folder. So you go to choose file, and that should open up the file explorer for you. Let's see, documents. I'm going to click through until I get to this lab folder. Hopefully you've already downloaded everything from Beachboard. You would just click on R, the chapter 13 R, chapter 13 practice problems, and this, more importantly, this chapter 1213 R markdown file from Beachboard that you've downloaded. And I think yours probably says this student underscore update. I think that's the file name for it. You will click open. I won't because I already have it, but you'll click open and then OK. You'll need to do that for each of these individually, unfortunately. It's like a little bit tedious, but you need to upload all of these into there. If you're using R, you don't need to do that. Instead, you'll just skip to the first line of code that we're going to run in the R Markdown script. So I suppose the first thing you should do is open your R Markdown. If you get a window that says, like, your computer doesn't know how to open this file or have a program associated with it, you probably haven't opened your RStudio yet. So open your RStudio and then try to open that file. Your computer should ask you, do you want to associate this with RStudio? Or it might just open it in RStudio automatically. So you need to download all of the files. So you need to download the Lab 8 Markdown and the Chapter 13 R and the Chapter 13 practice problems. The Chapter 13 R, let me see, did I name them something different? Okay, so you need the Lab 8 R Markdown, Chapter 13 practice problems, and Chapter 13 R. So the Markdown is the R file. The Chapter 13 practice problems and Chapter 13 R, those are CSV files, which we'll talk about in a second. They're essentially simplified Excel files. And that's where the data that we're going to use today is housed. Those are inside of those. So we're going to load these CSVs into R and then solve problems using the data. Okay, once you do that, let's see which one it is. Once you do that, for our Studio, once you open it, you should just automatically get everything opened up. If you're using RStudio Cloud, you then need to come over here to your files and open it that way. You can then close this console area. You can either click in the middle and drag it downward, or if you come over to right here or up here, you can click on this minimize bar. If you click on the big one, it makes the entire thing big. If you click on the little one, it makes it small. For when we use markdown files specifically, you don't need the console window open. So whether you're using RStudio or RStudio Cloud, you should get this window. This is what it should look like now. So this entire file is what is called an R Markdown file. And R Markdown files are essentially like a Word document that you can also code inside of. Regular R doesn't allow you to write text like this everywhere, but R Markdown files do. So it's a little bit easier, I think, for teaching purposes and probably in this online format in general. You'll notice a couple of things. So I've got these asterisks, these little stars. If there's one on either side, it's like this lighter blue color. And those are important notes that I've made. And you'll see those throughout. It's not a super noticeable difference. But if there's these double asterisks, then those are important terms or words that I will be using related to R. So those are essentially vocab words that you need to know when you're talking about R. Next, you'll notice that there are these like little hash marks, these like single hash, double hash, so on and so forth. Those actually break out sections. You'll see if you come over to the number line. So that's what this is. It's line number 1, 2, 3, 4, 5, 6, 7, 8. If you click those, you can actually like minimize everything. You don't have to do that. I'm just showing you that that's a feature of using those little hashes. And if you come over into the upper right corner of this main window, you'll see this little icon right here. And it says show document outline. If you click that, you get a document outline. It says intro to R, loading in data from CSVs. Let's get started with chapter 12 and 13, t-test, one-tailed, two-paired, homoscedastic, heteroscedastic, so on and so forth, right? So when you're going through your homework assignments and you can't remember, how do I do a paired t-test? How do I use a one-tailed t-test? What are the things I need to do? Worked example 2 was really helpful. I wonder, like, I need to look at that again. I forgot how it worked. You can click on that and it'll take you straight to that. You said, I don't remember how to load in files from a CSV. You can click on this loading in data from CSVs and it'll take you straight to it. Okay. So hopefully everybody is at this point now. Yeah, you can minimize all of these windows pretty much. So if you click here, you can drag that over to the side and have it as your entire screen. I don't recommend completely minimizing it. If you want, you can make this smaller and just have this one, or you can drag this over a little bit. This global environment part will be important to us in a little bit though. That's where we're going to double check that everything that we're saving as objects, so that's like one of the terms we're going to use, is saving correctly. But yeah, you can move things around as much as you want. Okay, so when we're starting with R, there are 2 ways to input data into R. You can manually input things where you just say this value equals 1, 2, 3, 4, 5, right? You can type numbers into Excel or into R, but that's super tedious and an easy way to make a lot of errors. So the way that we're going to be doing it is importing data from Excel. And we're going to be using these files called CSVs. And everything that I'm going to go through in class is typed out very clearly here. So please use this as a reference. So CSVs look like Excel sheets, but they're not a normal Excel sheet because they're actually a lot simpler. They don't have as many functions. And when you export and import them, they lose a lot of information. CSV just stands for a comma separated value also. So you need to make sure that whatever data sheets you're using are saved as .csvs and not .xlsx, these Excel sheets. And you do that by when you go to save an Excel sheet, clicking on Save As, and then from the drop-down menu, selecting CSV, right? It should usually just automatically do as an Excel. You'll have to go to the drop-down menu, select .csv. So I've already provided you 2 CSV files. That's the chapter 13 practice problems and chapter 13R. So the functions that we need to use when we load in CSVs are these file.choose, read.csv, and head. So if you haven't already, please download the files, get everything ready. And we're going to go ahead and use this file.choose. This is already typed for you. So this and pretty much everything else that is typed with these parentheses at the end is a function. And this function, this file.choose, opens up a search window that allows you to find a file and choose it, to choose the file that you're looking for and import it into R. So we're going to run this script, this function here, in this code chunk. The code chunk are all these gray areas. You can only code in code chunks. If I try to run this code, it's not going to do anything. Oh, I guess it does because this is a weird this is like a different type of format, but usually it wouldn't. But yeah, so you only run code in these code chunks. So let's run this file .choose. There are a couple ways to run a line of code. Way one, and the way that I recommend, it's a lot faster, is to use Control Enter on a PC or Command Enter on a Mac. Another way is to use this green arrow over here, and that runs the entire current chunk. Another way you can do it is click on this Run key at the top. If you click Run, you'll get a couple options. You can run the selected line, run the current chunk, run the next chunk, run all chunks above, run all chunks below, run all code in the file altogether. Probably you just want this run selected lines. You do not have to highlight the code to run the selected lines. Whatever line your cursor is on, wherever it is, if I click here and then run it, it will still run. Okay, so let's do that. I'm going to do Control Enter. You can do Command Enter. You can do either of those methods I just showed you. If you're using RStudio Cloud, you'll get this File Choose menu within RStudio Cloud. If you ran it using RStudio, you'll get whatever File Choose menu you usually get using your PC or your Mac. Don't run this multiple times. We went over this before when we first kind of like played with R that one day. There are three possible places that your files choose to have will pop up. It'll either pop up in front of RStudio like mine has. This is the best option. You might get a notification down in this bar that's like flashing and telling you you need to click something. If you click that, this will pop up. Or it may have come up behind your RStudio. If that's the case, you need to minimize it, click on it, do what you need to do in it. Do not run file.choose multiple times because you think nothing is happening. You will crash your computer. Your computer will freak out if that happens. Don't do it. Just calm down, look for it. It's probably popped up somewhere else. Okay. So the file that we're going to load in first is this chapter 13 _ r.csv. If you're using RStudio, you'll have to find it in whatever file you saved it into. If you're using RStudio Cloud, it's right here in your workspace. I'm going to click Open. Right underneath of that code chunk, I get this output. And this output tells me the exact location of my file. If you're using RStudio, it's probably a lot longer, and it starts with like desktop / your name / 260 / lab / whatever. It's probably really long. If you're using RStudio Cloud, it should look almost identical to this. Maybe you don't have this lab 8 folder. We want to highlight all of that, including the quotation marks, but not this one. This bracket 1 bracket, that just tells us there's one line to the output. I'm going to copy this. I use a lot of keyboard shortcuts. I'm going to use Control-C, or if you're using a Mac, Command-C to copy it. Or you can use right-click and copy. We're now going to paste that into this line here, line 38. And I say that right here, paste the output from the above into the parentheses and run the code below to load in your file. So we're going to paste that in these parentheses. You can use your mouse, you can right click, paste, or again, I like using a lot of keyboard shortcuts. I'm going to do Control-V or Command-V. I'm now going to run this line of code. Command Enter. It doesn't look like much has happened, but if you look over here into this global environment in the top right corner, you see now that we have a piece of data. We have a piece of data called chapter 13 with 23 observations of 8 variables. That's good. That's exactly what we want. So what this line of code does, because it's really important that you understand what these lines do and why we're doing them. We are creating something called an object. That's what this is. We're creating an object called chapter 13. We've decided to name it chapter 13. I will probably, for the most part, always have these 3 lines of code, like this line, and the next line we're going to run already written for you into your R Markdown files. But there may be times when you need to do them yourself, when you need to make your own objects. And it's very, very simple. So you type out a name that you're going to call your object. This arrow, this less than and then a dash, is an arrow pointing into your object. And then this read.csv function. This read.csv does exactly what it says. It reads a CSV. It reads a CSV file into, we're putting this arrow, right? We're putting this arrow, we're putting this function, this read.csv inside of chapter 13. We're reading the CSV file into chapter 13, our object. When we create objects, when we name objects in R, we never include spaces and never start the name with a number. Okay, so we have our object. It's called chapter 13. Now we should double check that R correctly loaded the file in, and we're going to use this head function. The head function prints out the first 6 rows of our CSV, of our object. It's a good idea to use this whenever you need to know the column names of your object, which you do. I'm telling you right now, you need to know the column names and to check that everything imported correctly. So I'm going to use head, or I'm going to use head to check chapter 13, this object. Control Enter. My cursor is on the line. Control Enter. And here we go. We have a column for males, females, juveniles, population 1, population 2, subject number, beef, and pork. And then the first 6 rows of data for each of those. Great. Now we can use this data to answer the questions below. All of these are not necessarily related to each other. I'm probably going to keep doing this. I think we'll see how this turns out. Where all of the data for the chapter is in a single file, like males, females, juveniles, those go together. Population 1, population 2, those go together. Subject, beef, and pork, those go together. These are 3 worked problems. These are 3 data sets for 3 worked problems, but I've included them in one CSV, and that is totally fine. And you'll see why in a minute. Okay. So now let's go ahead and actually move on to doing these F tests and T tests. And you'll see that it's not bad. It's actually pretty easy, and I think a lot easier and a lot faster than using Excel. So the functions we're going to use are t-test and var.test. Our t-test does a t-test. Our var test does a variance test, an F test. So let's break down this t-test, what goes inside of it. When we're running a t-test, we have to decide what kind of t-test we need to run, be that one-tailed, two-tailed, paired, homoscedastic, heteroscedastic. And we can do these in different combinations, right? We can have a one-tailed, we can have like a one-tailed paired t-test. We can have a two-tailed heteroscedastic t-test. So these can be kind of combined. Paired will always only go with one-tailed or two-tailed, never with homo or heteroscedastic. Remember, because we do not do an F test. We do not do a variance test when we're doing a paired t-test. In general, the code for doing a t-test is this line, on line 67. Our t-test function, so t.test, open parenthesis, data name, so our object name, in this case, chapter 13, $, group 1, comma, our object name, $, group 2. So data is the name of the data set you loaded in or you're working with, your object. In this case, again, chapter 13. The $, acts as a choose option, where we then choose the column name from the data set that we're working with, group 1 or group 2, right? That's just general. In this case, it might be chapter 13 $ males, comma, chapter 13 $ females, if we're comparing males and females from the chapter 13 data set. By default, this code will run a two-tailed heteroscedastic t-test. If you run a t-test and it just has this information in it, just data group 1, data group 2, it will run a two-tailed heteroscedastic t-test. That's not always what we want. Let's see. Okay, hold on, sorry. Hold on, sorry. Let's just keep going for a second. Okay. So by default, this code will run a two-tailed heteroscedastic test, which is not always what we want. We have to use arguments to tell R we want to use different t-tests. And we do, how do we decide what t-test to run? So again, we have to do these, we have to determine, is it one-tailed or two-tailed? We have to determine, are the variances equal or not? Or do we even have to do an equal variance test? If it's paired, we don't have to. Arguments are extra pieces of data that go inside of functions. So in this case, if we're hypothesizing that one group is greater or less than another group, we are running a one-tailed t-test, right? We have a directional test with the t-crit on the upper or lower bound, respectively. So we are running a one-tailed t-test, and we're going to use this argument called alternative. And it looks like this: alternative equals. And we either put greater or less. Greater or less refers to the group entered first in the t-test function and coincides with your alternative hypothesis. So if we are hypothesizing that the group we first enter, group 1, in the example above, will be greater than the second group, group 2, then our t-test code would look like this: t-test data $ group 1, comma, data $ group 2, alternative equals greater. This alternative equals greater tells R that we think our alternative hypothesis is that group 1 is greater than group 2. That's what this refers to. Group 1 is greater than group 2. If we were hypothesizing that group 1 was less than group 2, then our t-test would look like this. Be the same in the beginning, except our alternative would be equals less. And it's really important to remember that you need these quotation marks around that. So alternative equals quotation marks less. If we're doing a paired t-test, we're asking ourselves, are we testing the same individuals twice? If the answer is yes, we're doing a paired t-test. We need to specify that we're doing a paired t-test in the t-test function. And we do that with this argument for paired. We just say paired equals true. If we ran this, we would be running a two-tailed paired t-test. If it was also one-tailed, we could include the other argument as well. We could include in that also the alternative equals greater or less than argument as well, right at the end. And it doesn't matter what order. So for example, we could put it right here, alternative equals greater. Or we could put it before, alternative equals less, maybe. It doesn't matter. You just need to separate your arguments by commas. For equal variances, the first thing we need to do is an actual variance test, right? So if your answer to question 1 above was no, then we ask ourselves, are the variances equal? We have to do a variance test to find out. The code for the variance test is using this var.test function, but the input inside the parentheses is the exact same thing that we did for our t-test. So data, our object, chapter 13, $, our group name, or our column name, object, $, group name, or column name. Again, as I mentioned before, we will always be working with the right tail of the F distribution, which means our F-calc will always be greater than 1. If our F-calc is less than 1 when we run this test, then we need to switch our groups to report the correct F-calc, because it puts the variance that you put first on top of the second one. This is the numerator, this is the denominator. So the variance for group 1 in this case would be on top of the F ratio, and group 2 would be on the bottom. If the F calc reported after doing this test is less than 1, I would need to switch them. Group 2 would go here, group 1 would go here. If our p-value is less than 0.05, then our variances are unequal, meaning we reject the null hypothesis that the variances are equal, and we run a heteroscedastic t-test, which would look like this. Our t-test function, the data for data, $ column 1, data, $ column 2, var dot equals false. We're saying the variances are not equal. So var equal is false. Technically, we don't need to include this argument if our test is heteroscedastic, because that's the default. That's what t.test automatically assumes, that it's two-tailed and heteroscedastic. However, if we did accept the null hypothesis for our f-test and we find that our variances are equal, our var.test p-value is greater than 0.05, we need to do a homoscedastic t-test, and we do need to put this var.equals true into there. Now it is necessary. Now we have to put it in. Otherwise, it would automatically assume that the variances were unequal. Okay. So let's do some worked examples. Let's see, quick pause. Okay, never mind, cool. Okay, so never mind. So we've got our worked examples. Let's go through those. So this one is from page 133. So we're going to compare the weights of male and juvenile cactus wrens. We predict that the male cactus wrens are larger than the juvenile cactus wrens. So let's create our null and alternative hypotheses. Our null hypothesis, we're saying that our X bar males, our mean for males, is less than or equal to, oh wait, I think I got this backwards. Are larger. Oh no, that is the alternative, or the null. So our null hypothesis is that our X bar for males is less than or equal to our X bar for juveniles. The alternative hypothesis is that the average weight of the male wrens is less than or equal to the weight of the juvenile wrens. Our alternative hypothesis is that the mean weight of males is greater than the mean weight of juveniles. So that's the hypothesis we're actually interested in. So yeah, mean weight of males greater than mean weight of juveniles. We're going to test this using a two-sample t-test, but first we need to ask ourselves a couple of questions to figure out what t-test we need to use. First, are we testing the same individuals twice? see, I'm gonna ask that you type in the chat for these. Cool. No, yeah, we are not testing the same individuals twice. We're testing two different sets of samples, right? Two different populations, essentially. So no, we are not testing the same individuals twice. Unpaired t-test. Are the variances equal? Well, first we need to do a t-test to figure that out. So we're going to use this var.test function. So again, we need to specify the columns in R, and it might actually even help to double check what those column names are. We can actually run the head function again if we forgot what the column names to call those were. But first, let's write out our hypotheses for our f-test. So our null hypothesis for equal variance test is that the variance for males is equal to the variance for juveniles. I'll just type it all the way out. Our alternative is then that the variance for males is not equal to the variance for juveniles. Okay. So let's run the code above, and you can just, I've given it to you this time. In the future for, practice problems and stuff, I won't, but it's right above here. I do, however, recommend you practice typing it out. I've done this a lot, but I recommend you type this out to get it into your muscle memory, to really understand what you're typing. If you just copy and paste every time, you're not going to remember it. And when I give you an exam and you need to type out code, you're not going to remember what order things go into and how to do it. So let's just do that. var.test. You'll notice when you start typing it, RStudio already knows that you have this data set that you already imported called chapter 13. It says, that's probably what you're trying to type, and it automatically highlights it. Once you're there, you can just hit tab. And RStudio and RStudio Cloud will automatically autofill the rest of that. $. As soon as I hit $, RStudio is like, oh, you want to call a column from chapter 13. Here are those options. Here are the column names from chapter 13. We're comparing males, and then we can do chapter 13 again. Also, sorry, a really, really important thing to keep in mind is that R is case sensitive. If I tried to type chapter 13 like this, RStudio still knows, like, oh, you probably mean this. But if I then do a $, with this lowercase c, and then juveniles, let's just run that, I get an error. And it actually tells me, read your errors. Also, another just pro tip. Don't just freak out because it's red and it's scary. What does the error actually say? There's an error in your var.test default function. Object chapter 13 not found. Well, that's weird because I have chapter 13 right here. But remember, R is case sensitive. Chapter 13 with a lowercase c is not the same thing as chapter 13 with a capital C. So let's fix that and now run the code. And we get an f-test output for everything, right? If we were doing this in Excel, we'd have to calculate F, we'd have to calculate DF, we'd have to calculate this, we'd have to calculate the p-value, we'd have to calculate everything. Using R, we just need this single function and these two pieces of information, and it calculates everything for us. So this is an f-test to compare two variances. It tells us what data we're looking at, males versus females. We get our F ratio, which should already be sounding some alarms, right? This should already look like an issue. We have our degrees of freedom for our numerator and our denominator, our p-value, which is 0.4723. It tells us what our alternative hypothesis is. Our alternative hypothesis is that our true ratio of variances is not equal to 1. It creates a 95% confidence interval for us. And it gives us the sample estimates again, the ratio of variance. Here, it reports the F ratio again. Looking at this, we see that our p-value is greater than 0.05, which means we accept our null hypothesis and our variances are equal. However, we can also see that our F-calc is less than 1, which means we're looking at the left tail of the distribution, and we don't want that. Remember, I told you, I want your F-calc to be greater than 1, greater than or equal to 1. I want the larger variance on top in the numerator, not the denominator. So what that means is that we need to switch the two arguments. It means that the variance for juveniles is greater than the variance for males. So we need to put that one first. So var.test, chapter 13. Again, remember I start typing out, R already autofills it. It's already highlighted. I just hit tab. $, juveniles first. It's highlighted. I just hit tab. So much faster than typing it out. So much less likely to make errors like spelling mistakes, capitalization. Yeah. Comma, chapter 13, tab, $, males. Tab, it's already highlighted. Control, enter. So now we get the same output that we had before, except now we see that our F-calc is greater than 1. We get 1.447. But if we look at this and we actually can compare it to the one above it because it's still there, our p-value is the exact same thing. Our p-value hasn't changed, but now we're on the right side of the F distribution and our F-calc is above 1. And that's the F-calc that I want you to report for this class. Since our p-value is greater than 0.05, we accept the null hypothesis. Our variances are equal. We can do a homoscedastic t-test. So now let's do it. Let's do a homoscedastic t-test. We're going to use the t.test function. Again, by default, this runs a two-tailed heteroscedastic t-test. That's not what we want. We're running a one-tailed test, and our data is homoscedastic. We need to tell R both of those things. And I have that written out in here for you. Again, how you use the alternative argument. In this case, we're saying alternative equals greater or less. Honestly, it depends on what order you put these in, right? I'm going to put males first. But it doesn't matter, honestly. As long as your alternative equals corresponds correctly. So we're doing a t-test, chapter 13, males, comma, chapter 13, $, juveniles. So I'm just hitting down, down, tab, comma, and I'm putting spaces in here. They're not necessary. I personally, everyone has a little bit of a different coding style. I personally like to put spaces in because it makes it easier for me to read. But doing this is the same thing. It doesn't matter to R. Alternative. Again, RStudio already knows what I'm trying to type, and it's trying to autofill. It says you want to do alternative equals, right? Yes, I do. Thank you. So I'm going to hit tab, open parentheses. Remember, don't forget the parentheses. I'm going to write greater because I believe my alternative hypothesis is that the males are greater than the juveniles. The males weigh more than the juveniles. Close parenthesis, comma, space is optional. var.equal. var.equal is true. And that's it. That's the line of code that we're going to run to do this t-test. We're doing a t-test. We're comparing males and juveniles from the chapter 13 object. We believe that males are greater than juveniles, and the variances are true, or the variances are equal. Control, enter, right? You can have it highlighted or clicked anywhere on this line. It doesn't matter. Control, enter. And we get the output for our two-sample t-test. If we were doing this in Excel, we'd have to calculate everything, right? We'd have to calculate our means, our standard deviations, our t-crit, our p-values, our calcs, all that stuff. You don't need to do that in R. This is all you need. It tells us we're doing a two-sample t-test, the data that we're using. Our t-calc is right there. It gives us our degrees of freedom and our p-value. It tells us what our alternative hypothesis is. True difference in means is greater than 0. That's the same thing as saying that males are greater than juveniles. It gives us a 95% confidence interval. Although I need to double check why it does this. I think it's just saying that it's a very large value. The variances weren't unequal. We accepted the null hypothesis for the variance test, which means that the variances are equal. If we come back up here to the f-test, our alternative is that the variances are not equal to 1. We did not accept the alternative. We accepted the null hypothesis. That means our variances are equal. Yeah, okay. Where was that? Here we are. And then it gives us our sample mean estimates. So our mean of x and mean of y. Mean of x in this case refers to the first value entered. So males, the mean of males is 42.25. The mean of juveniles is 39.55. So it gives us all of that information just with this line of code. So what are our conclusions? Do we accept or reject our null hypothesis? Is our p-value less than or greater than 0.05? It's less than, which means that we reject our null hypothesis. And I want you to tell me why, right? So not just reject the null hypothesis, say our p-value is less than 0.05. Or you could even say, because it gives you an exact p-value, you could just copy this up here. You can just click this, copy it. And remember, I did Control-C. A lot of people, I think, were wondering how I'm so fast with typing. It's just keyboard shortcuts. So Control-C, Control-V to paste. So you don't even have to do this p-values less than 0.05. You can just say reject the null. P-value is equal to 0.007803. Biologically, what does that mean? Comparing our males and juveniles, going back to the original question, we were looking at male weight versus juvenile weight. We rejected our null hypothesis. What does that actually mean? If someone could type that into the chat, please. Yeah, males are heavier. Males weigh more than juveniles. And that's it. Now let's see if we changed our alternative to less, just for fun, just to see what it actually does. So we have everything is exactly the same as before. Males, juveniles, alternative equals less. So now this says males are less than juveniles. Our variances are true. Our variances are equal. We get all of the same values except for our confidence interval has changed. Our alternative hypothesis has changed, and our p-value has changed. Our p-value is now the inverse. It's the opposite of this value. Right? So this is, so if you get, well, no, I don't want to say that actually, never mind. Yeah, but yeah, so this is just another thing to keep in mind, that you need to make sure that your alternative less or greater corresponds correctly to the order that these are in. Okay. So worked example 2. And you'll also notice, sorry, that these don't give you a T-crit. You will have to look up a T-crit on your table still. Or using Excel, I suppose, but yeah. Okay, worked example 2. So this is on page 136. So now we're seeing how diet affects cholesterol levels in 10 different adults. For the first 20 weeks, all individuals eat beef. And then for the next 20 weeks, all individuals eat pork. We want to know if there is a difference in the cholesterol levels between the two diets. What are our hypotheses? So we're not asking, does one cause cholesterol to be higher compared to the other? We're just saying, is there a difference between the two? So our null hypothesis, and yeah, so our null hypothesis is that our X bar for beef is equal to X bar for pork. Or you could also technically say that the mean difference between beef and pork is equal to 0. It's a little bit longer to type out. But that's truly what we're actually going to be testing, right? Our alternative then is that our mean between the beef diet is not, or between the beef diet and the pork diet are not equal. So X bar pork. Or mean diff between beef and pork does not equal 0. So again, we need to ask ourselves a couple of questions. Are we testing the same individuals twice? Yes or no? Yes, exactly. And that means that this is a paired t-test. So is this hypothesis directional? I kind of already gave it away in these hypotheses. So no, it's not, right? We're not saying is one bigger than the other. We're just saying, is there a difference? Just asking if there is a difference. Again, the t-test function automatically does a two-tailed, unpaired, heteroscedastic test. None of that is what we want. So we need to tell R, using the t-test function, using the paired argument, that we need to do a paired t-test. And I have the code for that right here written for you. But again, I recommend you type it yourself. So t.test, open parenthesis, chapter 13. It's the same object that we've been working with this whole time. But we're going to use different columns now. So we're not going to use this male, females, juveniles. We're going to look at beef. And we're comparing that to pork. So chapter 13, it's highlighted. I press tab, $sign. I use the arrow keys and I scroll down to select pork. It's highlighted. I hit tab, comma, paired equals true. Control enter. And there it is. It does our t-test. So it tells us our data, our t calculated value, our degrees of freedom, our p-value, our alternative hypothesis. True difference in mean is not equal to 0. Gives us a 95% confidence interval and a mean of the differences. So that's a little bit different than what we got up here. This gave us the mean of X and the mean of Y. Now it's giving us the mean of differences. So the mean difference between beef and pork diets is 20.5 cholesterol units. I don't honestly remember what they were. So what are our conclusions? Statistically, do we accept or reject? Yeah, exactly. We reject because our p-value is less than 0.05. Good job. So reject, be null. P less than 0.05. Or you could even just enter the p-value. So highlight, Control C, Control V, paste it, or Command C, Command V. Biologically, what does that mean? Are cholesterol levels between beef and pork the same or different? Yeah, exactly. They are different. cholesterol levels between beef and pork diets are different. It's a little interesting here because we can actually just look at this, and even though it wasn't one-tailed, we can say what the difference was. So how are they different? In other words, how do they differ between? Looking at this mean of differences, we see that it's positive 20.5. What that tells us when it calculates this difference is that it's doing the difference of beef minus the difference of pork. If we get a positive value, that means the beef diet cholesterol levels are 20.5 points higher on average compared to pork. So we can actually say that. Rather than just saying they're different, we can say that they are significantly higher. Basic. Have cause, I don't know. Cause is probably appropriate here. Significantly higher cholesterol than pork diets. If we ran that exact same thing, that's exact same code as line 238, but we switch the order of pork and beef, everything is exactly the same. Our T is now negative, and our mean of differences is also negative, which means that pork is on average 20.5 points smaller than beef because it's doing pork minus beef. Our p-value and degrees of freedom, though, are the same. Okay. And the last worked example, this is not in the lab manual. So an entomologist is interested in two geographically separate populations of beetles. She's measuring antenna length in population 1 and population 2. Does your data suggest there's a difference between the two populations? So what are the hypotheses for our main test? This is non-directional. So we're just saying, is there a difference? So X bar pop 1 is equal to X bar pop 2. We're saying are the mean antenna lengths for population 1 and population 2 are the same thing. Our alternative is that they're not equal. 1 is not equal to X bar pop 2. Are we testing the same individuals twice? Yes or no? No. Yeah. Good job. We are not. Unpaired t-test. Are the variances unequal? Or are the variances equal? So what are our alternative and null hypothesis for the variance test? The null hypothesis is that the variance for pop 1 is equal to the variance for pop 2. The alternative is that they are not equal. So pop 1 does not equal the variance for population 2. We now need to do this variance test. Hopefully you've got the code down a little bit, right? So var.test. Where is our data? It's in chapter 13, that object that we created earlier, chapter 13. $sign. Let's look at the columns. We're comparing population 1 and population 2. So scroll down to it, highlight it, tab, comma, chapter 13, $sign, scroll down to population 2, tab. That's it. Control Enter. So we've got our F calc is smaller than 1. That already tells me that I need to switch these. I'm going to go ahead and just do that. Pop.2. I guess I just change that. Pop 1. Control Enter. And you can see just like that, it switches everything. So our F is now greater than 1. So we're on the right side of the F distribution. We have our degrees of freedom for our numerator, our degrees of freedom for the denominator, our p-value, alternative hypothesis, and our ratio repeated again. What test are we going to be doing? Is it one-tailed? Is it two-tailed? Are the variances equal or are they unequal? Two-tailed, yeah. What about the variances? Are they equal or unequal? No, not unequal. Our p-value is still greater than 0.05. It's close to 0.05, but it's bigger than it. Yeah, so we're saying that our variances are equal, kind of just barely, but equal enough. So we're doing a two-tailed equal variance t-test, which is the same thing as a student's t-test, or a homoscedastic t-test. So let's go ahead and do the t-test. So t.test, open parenthesis, let's enter in the data. So chapter 13, $, we're comparing population 1 and population 2. Oops, that's fine. See, two-tailed, which means I don't have to put anything in about tails. It'll do that automatically. That's the default. But we do need to specify that our variances are equal. So var dot equals true. Our variances are equal. Control, enter. We get our t-crit, degrees of freedom, p-value, our mean of x and our mean of y. So what are the conclusions of our t-test? Statistically, do we accept or reject, and why? Yeah, we accept the null hypothesis because our p-value is greater than 0.05. I think I just copied it. So our p-value is equal to 0.0638. Biologically, what does that mean? What is the question? I don't even actually remember. Population, antenna length in population 1 and population 2. Is there a difference between the two populations? We're accepting the null hypothesis, so we say no, there isn't a difference. There is no difference in antennae length. I think, I don't know. I'm probably spelling that wrong. No, antenna. An antenna length between POP1 and population 2. Great. Are there any questions about that? I hope that that was pretty straightforward. I know that R is scary. Believe me, it took me years to finally get the courage to start trying to learn R, but it is such an important skill. Oh my gosh. If you're doing any sort of analyses in the future, what you learn in this class is a skill you can put on your resume. You can put this on your CV. You can say that this is something you know how to do. And this is something I tell you right now, I'm applying for PhD programs right now. And this is something people keep asking me if I know how to do this. They say, do you know how to use R? Can you code? Can you do some statistics in R? And I can proudly say yes, which is great. And it looks great. It's a great skill to have, and it makes it so much easier in the future to learn how to do more complicated things. It's hard, it's scary. It's like, yeah. It really is low key fire compared to Excel. It really is. I know it's like a scary thing to do, but like it's so much faster once you get over how intimidating it can be. So, oh, okay. So if you want to enter your own coding chunk, you can do that. You can type the like little dashes and then the braces and stuff. The fastest way to do it, let me just do it here. The fastest way to do it, you have a couple of options. If you come up into this right area, you can do this insert. And these are different coding languages. Don't worry about that. We're just going to do R. That's one way. You can also, I think, no, that's not it. I'm trying to remember what the keyboard shortcut is. It's like I use all these shortcuts all the time and I never actually think about what they are. I just kind of do them. I think it tells you. I don't know. How do I do it? How do I enter a code chunk? There we go. Okay. Control Alt I is how you do it on a Mac. So it's probably Command Alt I on Macs. And you can type your own notes. Please do. If you are confused by anything, please like type whatever information you need to have in here. Another place you can type notes that I sometimes find really useful is in your code chunks. So maybe right here, I'm like, I want to remember something. If you do that, you have to put a hash before it. The hash tells R, everything that comes after this is for me, not for you. It tells R to ignore every bit of information that comes afterwards. So I can say variances are unequal or are equal. Need to remember to include bar dot equals true. You can write little notes for yourself inside of these coding chunks, but you have to put hashes. And you could put that afterwards. You could put whole like paragraphs if you want. But every line, every new line has to have the hash. T.test is a great function. I love R. Excel sucks. You know, like whatever you want in here. Actually, control. And if I left all of that in here and I run this, it doesn't change anything. R ignores all of this. Okay. So we're actually going to do a little bit of a lab activity. We're probably not going to have time to get through everything today, unfortunately. I do have a key for all of this, though. I will post the key so that you have the answers to everything. And everything is written out in this exact same format for every problem. It's the hypotheses for your main test. Are you testing the same individual? Are the variances equal? Do the test. What test are you performing? Do the main test. What are your conclusions? They're all broken up into the exact same steps. So we're probably not going to have time to go through all of these today. And we are doing a little activity that we thought would be kind of fun, just to like, you know, mix things up a little bit. We're going to collect data on our heart rates. I'm going to give you a Google Sheets, a Google Sheets file to type in your heart rates for. So, and while I get everything together for that, you can work on your practice problems in your groups. Then I'm asking you, please talk to each other. Please work together. Please. Okay. So pretty much what you're going to do is you're going to take your heart rate and you're going to do that by placing your middle and index fingers on the inside of your wrist or right on the middle inside of your wrist below your thumb. Oh yeah, like below where your thumb ends. That's strange. Okay. And you're going to hold it there and you're going to move your fingers until you can find your pulse. You're then going to start a timer and count the number of pulses you feel for 30 seconds or for 20 seconds, multiply that number by 3, and that's your heart rate per minute or your beats per minute. And then I'm going to ask you to do a little bit of exercise. Nothing crazy. Do some jumping jacks, run in place, run up the stairs, do some squats, whatever. Do some push-ups, whatever you'd like to do. Once you've just for 1 minute. Once you've completed your exercise, do the same thing, count your pulse, multiply it by 3. I'll then ask you that you record your heart rate before and after exercise on the Google Sheet that I'm going to provide for you. And then once everybody's finished loading their data in, I'm going to create a CSV from that, and we can load that in and actually work with our data. We can come up with our own hypotheses and figure everything out. So getting some real-time data. So before we do this file.choose file, and I think I named it something a little bit different than this, so it's whatever it's actually called. So we're going to upload file choose. It opens up this file choose window for me. Going to my my MS 260 fall 2020 lab 8. And I called it this Bio 260 HR data sheet 1. So it's a CSV file already. I'm going to open it. Okay. And now it's uploaded into this file window. Again, if you're using RStudio, you didn't have to do that. Now we can use this file.choose. Your window will come up, or you'll get the window essentially that I was just using if you're using RStudio. You'll click on the CSV or the file that you want, open. We get the file address. Remember, we did this at the very beginning of class when we started doing this. We get our file address. We want to select the entire thing, including the quotation marks, but not this one at the beginning. Copy, so Control C. Put that inside this read.csv function, and I've given you these, and I probably will for future R markdowns as well, and they'll be right here in this order. Control Enter. Control V to paste it inside, or right click and paste inside this function. Now Control Enter runs the function. Now if I look over in the global environment, we have a new object called HR for heart rate, 24 observations of 2 variables. That means 24 samples of 2 variables, right? Before and after. So what are our hypotheses? And we can actually kind of discuss this, right? Are we saying they're different? Are we saying something is bigger? What are we saying? So you can unmute or you can type in the chat, what do we think our hypotheses should be? Yeah. So one option for our alternative is that there is no difference. So before heart rate, or before, we should say mean, right? Mean before heart rate equals mean after heart rate, right? If that's the hypothesis we're going with, what should our alternative hypothesis be? Oh, I guess, Laura, you said it already, that they won't be the same. Yeah, so that they're not equal. So mean before heart rate does not equal the mean after heart rate. Okay, so those are not wrong. Don't get me wrong. Those are not wrong. But from what we know about physiology and heart rates and what happens when we exercise, could we be more specific? Do we have any predictions about what we expect our heart rates to actually do before and after exercise? Yeah. Our after heart rate should be higher than our before heart rate. And we can see that. You probably saw that when you were typing in your data and when you did it yourself, that your after heart rate was higher. So a more specific hypothesis might be that our mean before heart rate is greater than or equal, would be our null hypothesis, to our mean after heart rate. And our alternative, the one that we're actually interested in, the one that everybody is saying in the chat right now, is that the mean before heart rate is less than our mean after heart rate. So that's the one that we're interested in. And by default, because between the null and the alternative, we have to cover all possibilities, that means that the null is that it's either greater than or equal to the after. The before is greater than or equal to the after. Okay. Did we test the same individual twice? Yes, right? That's pretty clear. We all took before and after measurements. So yes, that means we're doing a paired t-test. Are our variances equal? This is kind of a trick question with this paired t-test. Do we even test for equal variances if we're doing a paired t-test? Look at that last slide on the PowerPoint, or that flowchart slide on the PowerPoint. Yeah, we don't test for equal variances if we're doing a paired t-test. So we can just put, we can actually just leave this blank. You don't have to put anything there. So that's all we needed to know to determine what test we're going to do. So what test are we running? Is it one-tailed, paired, homoscedastic, heteroscedastic? We didn't test for variances, so I guess equal variances don't matter, right? So hetero or homo, scedastic doesn't matter. We're doing paired. Is it one-tailed or two-tailed? One-tailed. If we go with the second option, the more specific one where we expect that our heart rate after exercise is greater, we'd be doing a one-tailed. So let's do our test. So we got t.test. Our new object that we're working with is called HR, heart rate, $, and we get the column names. Oh, I guess the one thing I didn't do is run this head file. Let's do that really quick. So that's what the data looks like. That's what I made that CSV into. So we have our heart rate before and our heart rate after. And just looking at these, we can see that there's probably a significant difference between the two. So back to this, we got t.test, open parenthesis, HR for our object, heart rate, $. I'm going to type it again so that they pop up. We're comparing before to heart rate after. And I don't think we actually technically need to do this alternative, but we can because we have an a priori or before idea of which way it's going to go. So we expect that before is going to be less than after, right? Because remember, it depends on the order that these are in. If I'd put after here and before here, then alternative would equal greater. But because we expect before to be less than after, alternative equals less. Oh, and then paired equals true because it's a paired t-test. Control, enter. And there we get it. We get our t-value, our degrees of freedom. Our p-value is very, very itty-bitty tiny. We get, and our mean of differences, negative 36.04167. So there is a negative, on average, a negative 3.36 beats per minute difference between before and after. Before is 36 points smaller than after on average. Okay. So what is our statistical conclusion? Do we accept or reject, and why? Yeah, exactly. We reject the null hypothesis because our p-value is very small. I'm just going to copy it. Control V to paste it. Biologically, what does that mean? What does that mean about heart rates and exercise? Yeah, it means that they're not the same. It means our heart rate before exercise was lower. I mean, exercises causes heart rate to go up. Heart rate increases with exercise. Yeah, all of those. So heart rate increases with exercise. And that's it. Congratulations. That was an actual experiment that you just ran. You collected data on an experiment that you did, wrote out the hypotheses, and did the entire analysis in a couple of lines of code. So that's great. That's actually a really impressive thing to do. So the first thing you need to do is make sure that you have this chapter 13 practice problem CSV that's on Beachboard. It is different than the chapter 13 CSV that we were working with before. This one has data for the practice problems. So you input that the same way as we did before. If you're using RStudio Cloud, you'll have to first upload it, file choose. If you've already downloaded it from Beachboard, you should get a pop-up window where you will select it wherever you saved it. If you're using RStudio, you will not do that, and you'll just start with file choose. And then everybody, yeah. So once everything is in, we'll go ahead, do file choose. I will now select the chapter 13 practice problem CSV. I already have it loaded in here, but now I have the file location for it. I want to copy everything, including the quotation mark. So copy, and then paste that inside this read.csv function. We're then going to Control Enter, keyboard shortcut to read it in. And if I look at this global environment, I now have this chapter 13 PP, chapter 13 practice problems. We want to check what that looks like. And we've got our subject, handed, opposite, healthy patient, cancer patients, shallow subtidal reefs, deep subtidal reefs, fly number, left side, right side. That's what we have, excuse me, for this data. And those will correspond to each of the questions we're about to answer. So for question 2, you're measuring bicep circumference of the dominant handed and non-dominant opposite sides of 12 individuals at the gym. Is there a difference in circumference between the two sides? So this is a little tricky because logically we can say that handed probably has a larger circumference compared to the non-dominant, just from personal experience. However, this question isn't worded that way. The question is non-directional. The question is just asking if there is a difference, which means that this is a two-tailed hypothesis. So our null hypothesis is that the mean of handed equals the mean of opposite. Our alternative is then that they are unequal. Are we testing the same individuals twice? Yes, we are. That means this is a paired t-test. And because it's a paired t-test, if you look at your flowchart from the PowerPoints, that means we do not have to check if the variances are equal. So we can just leave all of these blank. What test are we performing? A paired t-test. We put in parentheses that it's two-tailed. And then we can just do the t-test. So t.test, the object that we created that has the data in it is the chapter 13 PowerPoint. So I'll start typing that in. R will autofill. It says you have two things that you could be typing, either chapter 13 or chapter 13 PP. The PP one is the one that we want right now. That's the one with the data for the practice problems. $sign so that we can select the column. And we're going to choose handed and opposite. Those are the two categories, the two columns that we're going to compare. Let's see, is there anything else we need to put in here? Yes, we need to include the paired argument. Paired equals true. Running the test, we get the output right below. So it tells us what data we included, our t-calc, our degrees of freedom, our p-value right there, and the mean of the differences. So the mean of the differences is the average, the mean of a handed minus the average of opposite is 0.5666666 repeating. So what are the conclusions that we can come to? Statistically, we will reject the null hypothesis. And then I want you to tell me why. We're rejecting because our p-value is less than 0.05. Biologically, we can say the circumference the circumference is significantly different between handed and opposite biceps. However, because this test kind of gives us a direction regardless, even though it's a two-tailed test, for these paired tests, I want you to tell me how they're different, in which direction they're different. We can tell that by looking at this mean of differences. It's a positive number, which means handed minus opposite is positive, which means handed is bigger than opposite. So we can add on to that. We can say that the data suggests handed biceps are larger than opposite biceps. For question 8, you're studying the body weight deviation from normal weight in healthy patients and cancer patients. Is there a difference in weight deviation between the two groups? So what's our hypothesis for the main test? We're just asking, is there a difference? So X bar normal equals X bar cancer. Our alternative is then that the means are different. X bar normal does not equal X bar cancer. Are we testing the same individuals twice? No, we're not. So this is an unpaired t-test, which means that we need to calculate our we need to calculate the variance and see if they are equal. So what's our null hypothesis for the variance test? It's that our variances between the two groups are equal. So the variance for normal is equal to the variance for cancer. The alternative is that the variance for normal does not equal the variance for cancer. And that is always how these tests are going to be. That's always what the hypotheses are going to be, equal and unequal. So let's do the test. var.test chapter 13 PP $, healthy patients, comma, chapter 13 PP $, cancer patients. So now we've got our F ratio, which is smaller than 1, which means that healthy patients has a lower variance than cancer patients, because when it calculates the F ratio, it puts the variance for healthy patients, the first one, the first object, the first argument that you put in on top of this one. So this is numerator and denominator. Because it's less than 1, that means that this one is smaller than this one. So we actually want to switch those for this class, at least. I always want you to report the F value that is greater than 1, which means you need the larger variance on top. Doing that, our p-value doesn't change, but our F ratio does. So we see our F ratio, our degrees of freedom for the denominator or numerator, denominator, our p-value states our alternative hypothesis, and again, our F ratio. Looking at our p-value, it's greater than 0.05, which means we accept the null hypothesis. What's the null hypothesis? The null hypothesis for an F test is that the variances are equal. We're accepting that. That means the variances are equal. Which means, so let's write that out. Variances are equal. P-value is greater than 0.05. Which means that we're going to do a homoscedastic t-test. This is equal variance t-test, also known as a student's t-test. So let's go ahead and do that. T.test. Select the data, chapter 13 PP, $, healthy patients. The order doesn't matter for this one. But if you want, like, because it doesn't matter, you can put cancer patients first. That's absolutely fine. We need to include some extra stuff though. We need to include that the variances var.equal, using the var.equal argument, is true. Remember, if you don't include that, t.test, this t.test function automatically assumes that your variances are unequal. That's not true in this case. So we need to make sure that we're telling R the variances are equal. So we get our t-calc, our degrees of freedom, p-value, our 95% confidence interval, and the mean of x and the mean of y. Okay. So our p-value is less than 0.05. So we're going to reject the null hypothesis because the p-value is small. Biologically, what does that mean? What is the question asking again? So you're studying the body weight deviation from normal weight. Okay, that means that the average deviation is bigger for cancer patients. Deviation in body weight is different between cancer patients and healthy patients. I'm not saying that it's bigger here because we did a two-tailed test. I know I just said that because I was looking at the means here, but the actual question that this is asking is just two-tailed. It's non-directional. So we're just saying, is it different or not? And the answer is yes, the deviation is different between cancer and healthy patients. Okay. So you're interested in how competition between black surf perch and striped bass influences the body length of black surf perch. A previous research paper states that black surf perches that share space with striped bass have larger body sizes. Based on this, you hypothesize that competition, which occurs in shallow subtidal reefs, will lead to larger body sizes of black surf perch. So what are our hypotheses? It's actually a lot of times easier to write your alternative because it's kind of clearly stated. So let's actually do that one first. So based on this, we hypothesize that the competition will lead to larger body sizes of black surf perch. So say X bar shallow subtidal reefs, which is where competition occurs, greater than X bar, I believe it's like deep water. Let's check real quick. Chapter 13 PP using the head function. I just want to see what the column is again? Deep subtidal reefs. So I was just double checking what the column names were. So is bigger than deep subtidal reefs. Low competition. So between our null and our alternative hypothesis, all possibilities have to be accounted for. So if we're saying that in shallow subtidal reefs is going to be greater than, that means less than and equal to have to be in the null hypothesis. So X bar shallow subtidal reefs is less than or equal to X bar deep subtidal reefs. Are we testing the same individuals twice? No, this is an unpaired test. We're testing individuals from two different areas. Are the variances equal? Well, let's find out. So var.test, chapter 13 pp, $. Let's scroll down to this shallow subtitle, comparing that to the deep subtitle reefs. Looks like our F value is less than 1, so I'm going to switch them. And I'm just double tapping to highlight the entire thing. Just typing the first 3 letters and it pops up with everything else. And there we go. Our value is greater than 1, but everything else is the same. So we've got our p-value, which is smaller than 0.05. So let's say reject the null. P-value is less than 0.05. That means that we're going to do a heteroscedastic one-tailed t-test. That is specifically the test that we are about to do. So let's do that test. So t.test, chapter 13 pp, $, shallow subtidal reefs, comparing that to the chapter 13 pp. Oh, whoops. $, deep subtidal reefs, comma, now we have to put some extra information in, right? We need to include some details that the variances are unequal. So false, the variances are equal. We actually don't technically have to include that because t.test assumes that they're unequal by default, but I'm going to include it just for completion. Our test is also one-tailed, so we need to use the alternative argument. Remember that the alternative argument either takes greater or less, but those depend on the order that these have been put in. So we are hypothesizing that they're going to be greater. The body size is going to be larger in these shallow subtidal reefs with more competition compared to the deep subtidal reefs with less competition. So what I'm going to put here is greater, because we're saying this is greater than this. If these were reversed, if this was deep and this was shallow, then I would say less, because I'd say be hypothesizing that the size is less or smaller in deep compared to shallow. And we get our results. So we've got our t-crit, df, p-value, and the means. And we actually, just looking at the means, can see that our mean for shallow subtitle is actually smaller compared to our mean for deep subtitle. And that matches with our p-value, which is very high. So we will accept the null because of our p-value. And we can say that shallow subtitle surf perch are not larger than deep subtitle surf perch. These flies are known to be parasitic and typically attached to the cows on their right side. So you expect the bristles to be shorter on the right side. Test this hypothesis below. Okay, so we have a directional hypothesis already. We expect bristles to be shorter on the right side. So again, let's try that other method, right? We're going to write our alternative hypothesis first. So x bar right side less than x bar left side, right? We expect the mean length of bristles on the right side to be shorter than bristles on the left side. So our alternative, or sorry, our null hypothesis then is the opposite. It's everything except for this. So x bar right side is greater than or equal to left side. Are we testing the same individuals twice? Yes, we are. This is a paired t-test, right? So we have 12 flies. We're testing right and left side of each fly. That means that we don't have to worry about the equal variances at all. We can just come down here. This is a one-tailed paired t-test. So let's go ahead and do the test. We've got t.test. Let's enter in the data. So chapter 13 pp $. We are comparing left side to right side, or right side to left side. Either way, doesn't matter. This is paired, so let's include the paired argument equals true. And then we can do alternative equals, let's see, which one do we expect? We expect this one to be bigger and this one to be smaller. So we're going to say greater. We expect the left side bristle length to be greater than the right side bristle length. We find our t, our degrees of freedom, our p-value, and the mean of differences is about 1. So looking at our p-value, it's less than 0.05, meaning we're going to reject the null hypothesis. We just reject the null because our p-value is less than 5, less than 0.05. This means the bristles on the left side of the flies are longer than the bristles on the right side of the fly. And that's it. Okay, so that's it for solving all of these, but I do want to say a couple of quick things that might make using R a little bit easier, or a little bit, more fun, I guess, kind of. So let's just say this is some extra stuff. If you are ever using a function, right, we have the functions that we used today. We used file.choose. We used read.csv. We used head. We used var.test. We used t.test. I believe that that's everything that we used. If for some reason you are ever trying to remember what goes in here and you can't quite remember what does, if you type into one of these coding chunks, these gray boxes, if you put a question mark and then type the function and then run that line, so control enter, over here in this bottom area, this help window actually opens up. And it tells you about the function. And sometimes what comes up isn't super helpful. Usually up here, it'll tell you some things that go inside of it, what you can put in it, things like that, the arguments, all of that. So let's try that with the t.test. Tells us that it runs a student's t-test. And it tells you it performs 1 and 2 sample t-tests on vectors of data. And I'm actually going to show you how to do the 1 sample t-test really quick too. Here it shows you the default method. So x, y equals null. Alternative, you could do two-sided. Less, greater. Mu equals. if you're doing a one-sided, paired, bar equal, confidence interval levels, all of that stuff. It tells you the arguments that you can put into it, tells you some details, the values that it gives you. And if you scroll to the very, very bottom, you actually see examples. And again, sometimes these aren't super helpful, but they may just be enough to get you started thinking and remembering how to do these, how to use these different functions. So using the question mark before these, super helpful. One thing I wanted to show you also is how to do a one sample t-test. We've already finished the one sample chapter. So you don't technically really need to know how to do this, but I'm going to show you right now anyways. So let's just do this with the chapter 13. Let's do males, just males. We're not comparing it to another group, right? Because this is a one sample t-test. If we did males versus females, it'd be a two sample t-test. So maybe let's just kind of make up a hypothesis really quick. So I predict that males, or hold on, let's try this again. So it is known that males in another area weigh approximately 37 grams. I predict that do the males sampled weigh more than that? So I just made that up. It's not great. Let's say our null hypothesis is males equal X bar males equals 38. The alternative is then X bar males, let's see, way more than that. So I guess our null is actually less than or equal. Our alternative is that they weigh more than 38. Okay. That means that our mu is equal to 38. Mu, as we can see here in this help that I pulled up before, is actually an argument that we can put inside of a t-test. So if we do t.test, chapter 13 males, comma, mu equals 38, alternative, right, because this is a one-tailed test, equals greater. Because I'm saying that I believe that the males are greater than this mu of 38. Control Enter. And there we go. We have just run a one sample t-test using R. We get our t-calc, degrees of freedom, our p-value, our alternative hypothesis, true mean is greater than 38. That is what I have up here. That's what our alternative hypothesis is. And the mean of x. We see the mean is 42.25, which is indeed greater than 38. Okay. Last thing that I want to show you, totally unnecessary. You don't have to change this, but if you want to, you absolutely can. If you come up here to tools, then scroll down to global options and click that. Then come to appearance. You can change the way that your RStudio looks. You can change the font size to be a lot bigger if you want that. You can change the theme to whatever color scheme you want and that works for you. I personally like Crimson Editor a lot. I also really like Dracula. That's the one I usually use. What other ones do I really like? I like Material. And I like Tomorrow and Tomorrow Night, as well as Tomorrow Night 80s. Really, most of the Tomorrow Nights. So click Apply, click OK, and there you go. Your RStudio is now in a different color scheme. If you don't like it, you can always come back and try again to change it to something that you do like and that you want to keep. Sometimes having a dark theme like this is nice if you're working on things late at night. And that's everything. So I hope that helped, and I hope that you found these extra tips a little bit more helpful.